Hello and welcome to this video. We will learn about how to handle cash flows that you're uncertain about the values of their parameters. And we'll cover here the techniques called sensitivity analysis and break-even analysis. And these techniques are not only applied to cash flows, you can apply them in different settings and different aspects of project management and decision making. But we're looking here because of the course, it's engineering economics and management. So they can be applied in both, but we're putting them more in the context of engineering economics. So uncertainty is basically the lack of information. So when you lack information about something, this means that when you start planning for it, you assume values, and in the future, because you don't have the full information about this phenomena or this parameter, it will happen in reality with a different value than you assume. And that is a risk. A risk is a variation due to lack of information. Because if you know the information about the variation and what would be the possible variation in a parameter or in a system, then you will not have any risk with it because you will plan accordingly. This is the key here. If you're not certain about something, this translates into risk. In economical analysis of engineering alternatives, we need to do estimation here and predict values for things that will happen in the future, like how long the asset will live, or how much it will cost to maintain, or what's the revenue and the cost savings that it will create. So there are a lot of estimation here, and of course you cannot do a perfect estimation in terms of the accuracy of it. You can do your best to cover all the assumptions and make it realistic, but you cannot make it a true estimate in another way. So and the thing here that when we try to estimate a parameter and put a single value for it, we come here with two drawbacks. First, there is no guarantee that this estimated expected value will be the one that you'll see in real life. And there is no way to assess the outcome here of the risk with only one value. You have to experiment and try different values. So the approaches that we apply, present worth, future worth, annual worth, IRR, all of that, we're doing the analysis based on single values for the parameters we have. So there are different ways of handling decision uncertainty. This is just a list of some of them. There are a lot of ways you can model and handle uncertainties. So in this lecture and in this course, actually, we will cover three. Two of them will cover in this lesson, and then probabilistic analysis or probabilistic cash flow analysis we will cover in the next lesson. So the first one here is sensitivity analysis, and some people call it also what-if analysis. So it is a quantitative tool to assess how changes in a specific model parameter will impact the output of a model or a system. So if we're thinking here, in our case here, it's engineering economics, so cash flows, so present worth, annual worth, internal rate of return, anything that we use to assess the economic feasibility of a cash flow or an engineering alternative. If I change any parameter in my model, in my cash flow, how sensitive the outcome that I'm looking for will be to that change. So the procedure for sensitivity analysis, you have to select the parameter to analyze. You have to see, you can analyze all the parameters in the model, but that will be a big sensitivity analysis. So you have to select one, and you have to select it in a way that you assume that it's independent of other parameters, which might not be true in some cases, but here that is a very important assumption. Because what will happen is you will think about range and increment of changes in this parameter, and you start changing it and keep the other parameters fixed. So this is a key thing here. You assume it's independent and there is no correlation between the parameters you're analyzing here with respect to the other parameters that you're fixing. And then you select a measure of worth here for this cash flow. And so that's the output of the model, you can say, and calculate the measure of worth values at different increments or variations of that parameter you are analyzing. And then you look at the results and start the interpretation here, understanding really what's really happening here. So the best way is to actually graph it. So you'll have a graph and look at the graph and see which one, what is the sensitivity of the outcome to that change in this parameter. So we'll explain this process in this example here. So we have a cash flow and we have the most likely estimates, meaning that these are kind of what I expect to be it will change in real life, but I expect that's kind of to be the average or in the middle of the variation that will happen. One thing we need to do here is perform sensitivity analysis of present worth. So kind of it's selected to us this outcome over the variation range of negative 20% to 20% of each one of these parameters. So we'll be changing and looking at the sensitivity of the present worth of this cash flow if we change initial investment, if we change annual revenue, the annual operation and maintenance, the salvage value, service life, and the minimal attractive rate of return. So this is the cash flow as represented in the table we have seen before. 200,000 initial investment, 10,000 annual O&M, 30,000 revenue, and 75,000 salvage. You have 15 years, and your MARR, or what we'll use here as the time value of money, will be 5%. So if I put here the present worth formula, if I just use the kind of the pencil and paper approach, so it will be calculating everything, the value of this whole thing at the present. So 200,000 is the same as itself here, multiplied by 1. And then 75,000, I bring it to the present by P given F, 5% and 15 years. And then what I can do is actually calculate the net of the 30,000 and 10,000 because they happen exactly the same way. It's exactly the same look of this year. So they start at year 1, end at year 15. So I can get the net of it, which is 20,000 times P given A, present of an annual unit from Sears here, 15%, 15 years and 5%. So if you bring the factors from the tables, you find that the present worth here will be good news, positive 43,669. So that's the present worth of the most likely estimate cash flow. What we'll do is we'll construct this table for sensitivity analysis. So this value here that I calculated will be at 0 variation for all the parameters I have. So you see it's kind of repeated this way. And I need to complete the table because now I have this range of variation of values for these parameters. So let's see how we're going to do that. But let's see here, this specific cell here in the table refers to the present worth of the cash flow. If all of the parameters kept fixed to the most likely estimates, except for the annual operation and maintenance, that's being changed or reduced by negative 15%. So that brings it from 10,000 a year to 8,500 a year. And the others will be still the same. So this whole cash flow will stay the same, except for that value to be 8,500, and you can change everything here except for this value to be 8,500. Of course, this value here, the present worth of the most likely, will change. And the question is how sensitive it will be, how big change will it be for this parameter at this change or variation. If you look here, there are 1, 2, 3, 4 variations on the left, and then you have 6 parameters, 24 cases here, and 24 cases here, so that's 48 cases total you have to analyze. So have fun with doing all of that pencil and paper kind of approach to calculate 48 variations of this cash flow. So what we'll do is we'll use Excel. and we'll use its interest function. So the thing here, this lecture is mostly dependent on using Excel. And Excel is your best friend if you are an engineer, if you are, doing finance. It's amazing. It's kind of you can do programming with it, kind of. So I highly recommend that you keep that like Excel as one of the strong tools under your belt, because it will help you in your career in many ways. So enough with this career kind of mentorship kind of thing. So let's move on to how we're gonna construct that. So you can see here I'm using the Excel interest functions. So the present worth of the most likely case, which we calculate using the pencil and paper kind of approach, which is here, is matched with the interest formulas that I will use. And you can do a lot of things in cash flow analysis using just the function PV function here in Excel. So the present worth of the capital investment is just by itself. It's simple, negative B3, this value. And then I'm calculating the present value with B8, 5% time value of money, and B7, 15 years. And I'm leaving here this third parameter, PMT, which we'll see. And then I'm getting here a single sum, which is what we call here PFV in Excel. So this B6 is basically the salvage. So this is the salvage value part of the cash flow. Now let's move to the PV, just explain before we move to that one. So PV is a function to calculate the present value of something in the future based on a rate of interest or time value of money, number of periods. PMT is basically the payment, the series of payments. So it's kind of A that we covered, the uniform series that we covered in this class. And then when you see parentheses in Excel like this, then brackets here, this means it's optional. So you can actually skip and just close the function here if you're dealing with an annual worth and you're calculating present worth for it. But if you want to skip it, just, like we did here. In this case, we skipped PMT and we dealt with FV. FV is optional, meaning that you can actually calculate both present value of PMT and FV, or PMT only or FV only. So in this case, we're doing it like separate. So this is the present value of an FV, future value. And then the type here, it's an optional. I don't recommend playing with it, but because typically the standard is a cash flow is an end of year period cash flow. So already the default value 0 here is referring to end of periods cash flow. So don't worry about the type, because typically we're following the default case. So if we go now to this one, PV, you see these are the same, the time value of money, number of periods, and then I'm dealing here with the PMT, which is the difference between B4 and B5, which is the annual revenue and the annual operation and maintenance. And I close here. You see I close the bracket because I'm not covering FV here, which is already covered in the second term. So that's the function that I had it here and also here. So that's the dollar value here is not like the dollar. It's an Excel. You can fix the reference of a cell to tables or to arrows and columns. So if I drag these cells, $B means that I'm fixing the column here. So if I drag right and left, the reference to this B3, if I drag this one here, will stay the same, because I'm dragging columns and I'm fixing the column here to be, but if I drag it to the bottom here, it will change. It will actually change the reference of cell. So when I drag, it will drag with me the reference of the cells here. So the referencing cells in Excel is important, also concepts that will help you to accelerate and make things faster for you. Now, if we look here, now I'm showing one formula for one cell here, which is the same one we kind of explained in a previous slide or referred to. So the present worth, the thing here, if you remember it, I'm fixing everything. So you see the difference between the two formulas, the blue and the red. Everything is the same except for that, which is changing B5. B5 is the annual operation and maintenance. So I'm changing it by F3, which is 15% negative. So that's the formula for this cell. Does this mean that I do the formula here for every cell here? No, I actually can show you here. That's the Excel sheet, and I will skip that for now. Okay, so it doesn't want to move. So, but let's see here. If I delete all of that, I think you started screaming, "No, that's a lot of work. The video will be long." But it's not the case. If I drag this to the left and then to the right, it will construct it, like it will calculate the values for me. So the idea here is you use the right reference of the cells here. So I'm fixing here. So when I drag to the left, so this one, if you see, when I dragged it to the left, it didn't move these cells to the left, but it moved that cell to the left. So because I used the reference here, this H$3, meaning that I'm fixing the row, but I'm allowing it when I drag to change the column. So basically I can drag everything here to the left, drag everything here to the right, and boom, there you go. So let's get back this thing to the original format. So I'm here highlighting the base most likely estimate, and everything else is a variation by the range that I selected. So it's not a lot of work. It's just a matter of doing it in a smart way. Picking a cell that you know that with the right reference, when you drag it right and left, up and down, it will calculate what you wanted over all these cells. And that's the power of Excel, is you can repeat calculations for a lot of possibilities and a lot of values. So now if I plot these values, now I can see here, that's my most likely case, right? That's the zero variation for all parameters. And that's the value where I ended up with before. If I go back for around 44,000, it's around 43,000 here. And this is the region or the line where I accept or reject. So it's the zero present worth. If you remember, a positive present worth is good news, negative ones is bad. Because positive means you are getting return that's equal to or more than what you asked for in time value of money, and less is the other case. So you can see here in most of the variations, my conclusion doesn't change. Changes in all of the parameters will not change my decision at the end. It will reduce my return, but it will not be below my minimal attractive rate of return. So it will be mostly here accepting, and that will be an acceptable investment or alternative regardless of the most of the variation that happens, except for that orange one, which is the annual revenue. So the annual revenue here, the way I can represent that is that my outcome here is very sensitive to changes in annual revenue, which is mostly, in most of the cases, true for most of investments. Your revenue is the one driving, the engine driving that investment. So, but you can see here, it's until, the extreme case here of a lot of changes in revenue, you will start not getting your minimal attractive rate of return. But it's sensitive because you can see here the slope of the line is greater than anything else. And then if you can start classifying, you can say that's fairly sensitive to initial investment change in values. So that's another classification, fairly insensitive. And then the others here are kind of relatively insensitive. So my even the values here, yes, I'm still within the accept region, but the values of my present worth didn't change that much. So that's the outcome of sensitivity analysis. Is you plot this graph and you start looking at changes of my outcome by different parameters and their variations, start classifying them and really understand what's really the outcome here is sensitive the most to which parameter. And once you know that, then I know that I will do my best to make sure that the annual revenue is maintained at the level that I want. So I will pay more attention to it. So that was sensitivity analysis. The next is break-even analysis. So sensitivity was asking this question: how will changes in a specific model parameter impact the outcome of a model? So we start changing the parameters and see the impact of that. Break-even analysis is what's the balancing point between positive and negative cash flows at which a specific outcome I want will be achieved. And typically the outcome here is when when will be break and make point of this investment, where I will be making money at a point where after it I will make money and before it I will lose money. But in this case, in our economics, remember, when your present worth of inflow or positive doesn't equal or less than your negative present worth of the negative cash flow or the outflow, it doesn't mean you're really losing money. It means the return of that investment is less than your minimum attractive rate of return. So just clarify here, it's not like making money, losing money. It's more about if I'm, what's the point where I will achieve my MARR or not. So we kind of did this break-even analysis when we did the internal rate of return. IRR is a form of break-even analysis, and we'll see that as an example very soon. Break-even analysis is also like heavily used when you start sizing production lines and see like how much investment I will have to make and how much how big should be a production or how much usage I will have to justify that. I should have to justify that investment. So an example of that is like you're freshly grad and you're living in a big city and currently moving by public transit or by Uber or Lyft, and you're thinking about buying a car. The first question is how much I'm using it. I'll be using it, because that's a big question. How much you actually need the car. So the usage here is a key, because if you're using it a lot, then the return on that investment will be justified. So we will perform also break-even analysis, both kind of numerically, kind of pencil and a paper, and also using Excel, using the goal-seek function. So we'll see that. So we'll see application of break-even analysis in both internal rate of return case and a case where we size a production example or system. So here we have the same cash flow that we covered in sensitivity analysis, and we need to find IRR. So if, as a reminder, check the video on IRR that I did before. But IRR is the time value of money that makes the present worth of inflow equals to the present worth of outflow, or the difference between them, which is the net present worth, would be equal to 0. So what I do is I try different I's, time value of money. 6 is one of them, and you can see here 6 will give you 25,540 net present worth, which is the difference between present worth of the outflow and present worth of the inflow. I'm here showing the absolute value, so these values should be negative, and I'm defining here my outflow is just the initial investment. Operation and maintenance is an outflow, but I combine it with the annual revenue and kind of got the net of them, which is 20,000. So you're free to use annual worth, the annual operation and maintenance, to be part of your outflow, and in this case, this value here will be changing, will be different. But if I plot now these three series of values, so the orange is the inflow, which is that value you see it's decreasing with the increase of the time value of money. Outflow, like we explained, is just the initial investment, it's fixed. The present worth is at where it happens, so it's not impacted by the time value of money. And then the difference between them is that line, the gray line. And IRR is where this line intersects with the horizontal axis, or it's where these two lines intersect. So that's the point where my IRR exists. So now I know kind of roughly it's between 7 and 8% graphically or by looking at the numbers, but I can use Excel to figure this out exactly how much it will be by using what we call the goal seek. So if you go to data in Excel sheet and then press what if analysis, goal seek, and you set the cell that you want to change to, which is the time value of money, B9. The net present worth. You want to change it to 0, so you want Excel to change the values until it reaches 0. Change these values by changing which cell, and you're actually changing only the time value of money, which is 6. So when you change time value of money, the formula for net present worth will change. And if you do that, you'll find that it's changing that value to 7.6. So now I know that my RRR exactly 7.6. And if you use the data into the present worth formula we showed before, the most likely estimate cash flow, you will end up with exactly 0 net present worth. So break-even analysis, the most famous tool that's being used for is goal seek in Excel. And in break-even analysis, it's usually you're looking for a point of intersection between two functions. And these two functions represent inflow, outflow, or cost and revenue. So there are different forms you can apply break-even analysis. The last example we'll see here is sizing a production system using break-even analysis. So you have here this manufacturing firm is investing into a capacity expansion with this cost. The cost would enable the company to produce up to 100,000 parts. Question, should we fabricate or use this full capacity or less? So other parts of information here, each part would generate $2 net profit. So, excuse me, so with the production, there is a variable cost with it. So the more I produce, the more cost would be, like you need to hire people, you have to buy material, but also the more you produce, the more revenue you will have. So kind of it generates or it gives you here the net of both, the net of the revenue you generate and the cost that will happen because of your production. But there is a fixed cost here, 25,000. Regardless of your production, you are paying 25,000 a year. So, and also here you're given MARR to be 10%. So it's asking what is the minimal annual production volume to make for this investment, to make this investment justifiable. And you assume here salvage value to be 0. So this is the cash flow. Everything is known except for the net profit because it's dependent on the number of units you're producing. So the first approach is calculate the present worth of the outflow. So the red arrows here, negative 250 and then negative 25,000 times P given A, 10%, and you have 7 years. It will give you one single value. Present worth of inflow, which is this, is a function of the number of units you're producing, and using P given A, 10% and 7, so it's a function of N. Now to find N, you want to set your present worth of inflow to more than present worth of outflow, and that means that your production should be more than 38,176. So that's numerically using pencil and paper. Another way is graphically. So you use these formulas here, and you change N values to figure out the change in their values. So the present worth of outflow is fixed. It's not dependent on the number of units. But the inflow is dependent on the number of units, and this is where's the point where you will have good news here, bad news here. Good news because you're achieving your minimal attractive rate of return here. Beyond or before this point, so like 30,000 units, you're not achieving your minimal attractive rate of return. You're not using the system at the capacity that it can give you your MARR. The last thing here is how to use Excel. So goal seeking. So you will see here that's the calculations for present worth of outflow, present worth of inflow. All of that is an input. One thing I'm highlighting here is that volume of production or number of units. That's the variable that I will change, B5, to make the net present worth, B12, equal to 0. And that's the goal seek function. Once you click OK, it will change the values until from this value initial, or just a random value you start with, until it hits here the same value we ended up with before from numerical and graphical methods. So let's go back to Excel and break-even IRR. So that's basically the graph I'm showing. That's the calculations here of using the present value function. So I'll post that for students in the class to see it in action. But if I change, so you see this time value of money is 7.6. If I change it to 1, of course, my net present worth will be positive because if I undo, MARR or IRR is already 7.6. So if this investment can return 7.6%, if my goal is just to set it to 1, then of course you will get a big positive present worth, net present worth. Now, if I'm looking kind of starting from scratch, what's IRR? So you will go to data, what if analysis, goal seek, and you set the value of B9 to be equal to 0. And what you will be changing is your time value of money. And if we say OK, see the values changed. It found here the answer. 7.6. There you go. So that's the break-even when you will use it for finding IRR. If you use break-even analysis to size of production or determine the usage of an asset, this is the same example I showed in the slides, but showing here, this is the table that shows the different values of outflow and inflow at different N or production size. Now I want to do goal seek, so data, what if, goal seek, and you want to set this value, net present worth. Oh, wait a minute, I have to change that value to any arbitrary value, just make it not the value I'm looking for, 200. So of course 200 is here, so you're losing a lot of money here, man. So what happens is, what if analysis, goal seek, and I will change this value to be 0 by I'm looking to make this value equal to 0 by changing this value here, the production volume. And if I hit OK, and that's the same value I ended up with before. So goal seek is a very strong function in Excel, and it's very helpful in many applications, including break-even analysis. So we learned in this video how different ways of handling uncertainty in cash flow. Sensitivity analysis is a very known example of that. You don't know how to quantify uncertainty, so you just change the values and see what's the sensitivity of the outcome to these changes. Break-even analysis is not really dealing with uncertainty, but you're looking at predicting or countering uncertainty by sizing a system in the right way. So you make sure you're making the money you're seeking or you want, but it is a very useful tool in general, regardless if it's dealing really with uncertainty or not. But it is a very important tool when you're making when you are involved in decision making or heavy investment decisions. All right, thanks for watching, and I will see you in future videos. Take care and be safe.